Next application is op-amp as summer or adder. Here the operational amplifier is used to perform the addition operation. There are two types of summers, inverting summer and non-inverting summer. If the multiple inputs are given to the inverting terminal and the non-inverting terminal is grounded, that is called as inverting summer. Or if the multiple inputs are given to the non-inverting terminal and the inverting terminal is grounded, means that is non-inverting summer. First we will discuss inverting summer here, where the multiple input voltages are given to the inverting terminal and the non-inverting terminal is connected to ground here. So here the VA, VB and VC are the input voltages, the multiple input voltages given to the inverting terminal. They are connected through the resistors and called as R1, R2 and R3. So here we are going to connect one feedback resistor which is always connected between the output voltage and the inverting terminal voltage V2. I'll call this as RF. Current flowing through these resistors are current flowing through R1 I'll consider as I1, current flowing through R2 I'll consider as I2, and current flowing through R3 I'll consider it as I3. So the current flowing through this feedback resistor RF is IF. Function of this inverting summer is the output voltage will be equal to sum of all these input voltages VA plus VB plus VC along with the amplification here. That is nothing but which is depending on the passive elements RF, R1, R2 and R3 along with the amplification and the addition. So one more function is it will invert the input signal. After the addition along with the amplification, the output will be inverted here. We'll see how the output voltage will be obtained here by deriving the expression for output voltage. Again we should follow the same 4 steps. In step 1 we should find voltage at non-inverting terminal here. Voltage at non-inverting terminal is V1, that is connected to ground, so it is equal to 0 volts. Next step 2 is we should find voltage at inverting terminal. So voltage at inverting terminal is V2. From the concept of virtual ground we know that V1 is equal to V2, that is from the concept of virtual ground. So here V2 is equal to V1 is equal to 0 volts. In step 3 we should apply KCL at inverting terminal junction here. So if I am applying KCL at the inverting terminal junction, current entering the junctions are I1, I2 and I3. So we should take sum of all these currents where I1 plus I2 plus I3, and current leaving the junctions is feedback current IF, that is equal to IF. We know that there won't be any flow of current from this terminal to this terminal because input impedance is equal to infinity, which is acting as open circuit here. Now step 4, we should replace all these currents by voltages and resistance. So if I want to replace all these currents by voltages and resistance, this I1 current is flowing through the resistor R1 here. The potential drop across this R1 is VA minus V2. This junction and this junction both are same, so voltage at this junction and voltage at this junction will be same. Here also it is taken as V2. So potential drop across R1 is VA minus V2. So I1 can be replaced as VA minus V2 divided by R1. Next plus I2 can be replaced as VB minus V2 divided by R2. VB minus V2 divided by R2 plus I3 can be replaced as VC minus V2 divided by R3, that is equal to this IF can be replaced as potential across RF is V2 minus V output. V2 minus V output divided by RF. So now substituting value of V2 where V2 is equal to 0 here. So this equation will become VA divided by R1 minus 0 means I'll take it as 0. So it will be VB divided by R2 plus Vc divided by R3 is equal to minus V output by Rf. So if I'm taking this to the left hand side and taking this term to the right hand side, so this equation will become V output is equal to V output by Rf is equal to minus of Va divided by R1 plus Vb divided by R2 plus Vc divided by R3. Now if I am cross multiplying this Rf to the right hand side, V output is equal to minus of Rf divided by R1 into Va and again plus Rf divided by R2 into Vb plus Rf divided by R3 into Vc. So this is the output voltage for an inverting summer. Here Va plus Vb plus Vc, all the input voltages are added along with their gains here. So gain for this input voltage is Rf by R1, gain for this input voltage Vb is Rf by R2, gain for Vc is Rf by R3. So after adding all these voltages along with amplification, since it is inverting summer here, that is provided with the negative sign here. If we consider if R1 is equal to R2 is equal to R3, all these resistors are equal to same value R here. This equation can be rewritten as V output is equal to minus of, since all the resistors R1, R2, R3 are equal to R, I'll take common here. Here Rf is also common. So this equation will be equal to minus Rf by R into Va plus Vb plus Vc. So the output voltage of inverting summer is addition of all the input voltages Va plus Vb plus Vc along with the gain as Rf by R, and there is an inversion of this input voltage. So this is the output voltage of inverting. Is connected through the input resistors R1, R2 and R3, and current flowing through these resistors I consider it as I1, I2 and I3, and the feedback resistor Rf is connected between the output voltage and the inverting terminal voltage V2, and there will be input resistor for inverting terminal. So in this case, this non-inverting summer performs an operation of addition by adding Va plus Vb plus Vc along with the gain here. Since the input voltages are given to the non-inverting terminal, the amplification will be similar to, or the gain will be equal to same as the non-inverting amplifier, nothing but 1 plus Rf by R. We'll see how the output voltage will be obtained for non-inverting summer here. So again we should follow the 4 steps. First we should find the voltage at non-inverting terminal here. In step 1 we should find the voltage at non-inverting terminal. In this case, this non-inverting terminal voltage is connected to multiple input voltages. So in order to find the non-inverting terminal voltage, we'll apply KCL at this non-inverting terminal initially only. So apply KCL at non-inverting terminal in order to find the non-inverting terminal voltage V1. So if I am applying KCL, the current entering these junctions are I1, I2 and I3. Current leaving the junction, here it is open circuit, so the current leaving the junction will be almost equal to 0. So the KCL equation will be I1 plus I2 plus I3 is equal to 0. So if I am replacing these currents by voltages and the resistance, this current I1 is flowing through the resistor R1. The potential across this R1 is VA minus V1. So VA minus V1 divided by R1 plus this I2 is flowing through the resistor R2. It will be VB minus V1 divided by R2 plus I3 is flowing through R3, so it is Vc minus V1 divided by R3 is equal to 0. If I consider if R1 is equal to R2 is equal to R3 is equal to the input resistance which is connected at inverting terminal, if we are considering by assuming that all these three resistors are equal to R. So these three resistors will be equal to R. So if I'm taking common, it will be 1 by R into VA minus V1 plus VB minus V1 plus VC minus V1. So it will be 1 by R into VA minus V1 plus VB minus V1 plus VC minus V1. If I'm considering all the three resistance are equal to R is equal to 0. If I'm cross multiplying, R will be multiplied with 0, so that is equal to 0, and this will, the remaining term will be VA minus V1 plus VB minus V1 plus VC minus V1. So this will be equal to VA plus VB plus VC, and 3 times minus 3 times V1 is equal to 0. So we need the voltage at non-inverting terminal, which is nothing but V1, where V1 is equal to VA plus VB plus VC divided by 3. So in first step we found the value of non-inverting terminal voltage here. Next, in the second step, in step 2 we should find the voltage at inverting terminal, where V2 is equal to, from the concept of virtual ground, that is V1 is equal to V2 from the concept of virtual ground. V2 will be equal to V1, nothing but same value, VA plus VB plus VC divided by 3. Second step is finding the voltage at inverting terminal V2. In third step, step 3, we should apply KCL at inverting terminal here. If I'm applying KCL at inverting terminal, the current entering the junction is I here, and leaving the junction is IF, and current flowing through this terminal will be equal to 0 because input impedance is infinite, which acts as open circuit. I is equal to IF, and in step 4 we should replace these currents by voltages and the impedances or resistance. Current I is flowing through the resistor R here. Potential drop across this R is, since it is connected to 0, 0 minus V2, 0 minus V2 divided by R is equal to IF is flowing through the resistor RF. Potential drop across that one is V2 minus V output, V2 minus V output divided by RF. So if I'm rewriting this equation, minus V2 by R is equal to V2 by RF minus V output by RF. So if I'm taking this minus V output by RF to the left hand side and minus V2 by R to the right hand side, this will be V output by RF is equal to V2 by R plus V2 by RF. If I'm taking V2 common here, V2 remaining will be 1 by R plus 1 by RF, and left hand side V output by RF. And taking LCM of these two, if I'm rewriting this, V2 is into RF by R divided by RF into R. In the left hand side, V output by RF. RF and RF will get cancelled. The remaining will be V output is equal to RF by R plus R by R is 1 into V2, and we'll substitute the value of V2 here. V2 value is equal to VA plus VB plus VC divided by 3, where V output is equal to 1 plus RF by R. V2 value is VA plus VB plus VC divided by 3. So this is the output voltage for non-inverting amplifier, where it performs the operation of addition, where VA plus VB plus VC along with the gain here. Gain is 1 plus RF. Since the input voltages are given to the non-inverting terminal, gain will be equal to non-inverting terminal amplifier 1 plus RF by R, and 1 by 3 for the 3 input voltages. If we are giving only 2 input voltages, VA and VB, this denominator will be equal to 2.